Okay, so we have this formula for the likelihood of a model, and it's the probability of the data conditional on the model. So we'll have to be able to calculate this right-hand side. And we'll show in the next slide, thanks to Felsenstein pruning algorithm, how to calculate the probability of some data on the leaves given a tree. A topology plus branch length plus substitution model. So look at this tree on the left of the slide. It's on a certain site where we have a character A for one taxon and for the other taxon character C. The branch length are T1 and T2, and the root of this small tree is R, is labeled R. This is our whole model T, okay? So T is branch length plus implicit, plus topology, of course, this topology is very simple, and implicit substitution model Q. And what we see on the leaves, the data, D, is this aligned site A and C. What is the likelihood of the tree? It's the probability that this data, A and C, have been generated by this model. This model has time evolving from the root to the leaves A and the leaves C. What is this probability? This probability, and based on the fact that evolution is supposed to be independent on each of the branches, you see, once the two species, if we take the example of a speciation node with two species that evolve on one branch and on the other branch, once the two branches separate, then the evolution is supposed to be independent on each of the branches. So then the probability to have this tree is the probability to have some ancestral character here, being the same, obviously, for this branch and this branch. This ancestral character, the probability for it to evolve into A over a time t1, and independently to evolve into C over a time t2. This probability of this total phylogeny can be written like this. This is the probability a priori of R being labeled with the character I. And I, you will see, will take its values in A, C, G, or T. Okay? So let's suppose that we have a character that is called I here on the root. Then this character I must evolve into A over a time t1. So probability for I to transform itself into A over a time t1, or to evolve into A over a time t1. And also we must have I evolve into C over a time t2. So the probability is the product, the probability for this evolutionary history with I here, a character I here, is the product of the probability a priori to have I times the probability of transformation from I to A and probability of a transformation from I to C on this branch. And now, if you remember what we got from our model, if our model is a stationary model, if our substitution model is stationary, it accepts an a priori or background distribution of probabilities. So this probability of R being equal to I is pi I. Okay? It's given by the model. This probability, remember, of for I to transform into A after a time t1 is given by the analysis of the exponentiated matrix QT1, okay? Q multiplied by T1 is a matrix. Its exponentiation leads to a matrix also, and you take in that matrix the value that is on line I, column A, to get this probability. Similarly here, you get this information from the matrix E of QT2. And this is the probability to have this tree with I here. Okay, but you know you have 4 possible values for I, so you will sum the 4 probabilities corresponding to these 4 possible values for I, A, C, G, or T. And you have this sum of products as your full probability of the data, AC here, given the model, the 3, right? This is the likelihood of the model. Here the model is a 3. So we know how to calculate the likelihood. In this case of a very simple topology linking 2 leaves. Pay attention also to one thing, that we're having a product of elements or members, each of them being less than 1. Okay, this pi I is less than 1. The exponentiates of qt at a certain position is also less than 1, etc. These probabilities are all less than 1 because it's probabilities. So in reality, the probabilities are always very small. Okay. Likelihoods in a tree tend to be likelihoods for corresponding to a site tend to be very small compared to 1. Based on this example, a recursive procedure enables us to calculate the likelihood for more complex trees based on partial likelihood vectors calculated on the subtrees. Because if you see this, in fact, we have calculated, we extract from this very easily the partial likelihood of this subtree based partial likelihood corresponding to I being equal to A, that's this product with I equal to A, partial likelihood here of this tree with I equal to C, etc., etc. So based on partial likelihood vectors calculated on the subtrees, we calculate easily, we reuse what we've calculated here in the context of a larger tree. Imagine a larger tree where this is just a subtree of the larger tree. Okay. So that's how, thanks to Felsenstein's pruning algorithm, we are able to calculate likelihood values for large trees. And at the root of, at the core, sorry, of the Felsenstein's pruning algorithm is this relation establishing the likelihood of a tree given some exponentiations, some matrix exponentiations. Right, so in order to calculate, so see the slide before was based on the observations made on one site. But usually you build alignments, you infer phylogeny, based on not only one site, but an alignment of many sites. And the assumptions that is, the key assumption that is made is that these sites evolve independently from each other. We know it's wrong, we know it's not true, we know that and this independence is not true, especially if you consider nucleotides alignment, and you see that the sites that are in first codon positions do not evolve completely independently from the sites that are second codon position and third codon positions. These are linked. And even if you see the fact that then in a protein, active sites in a protein, active sites, or the structure of a protein is one that is folded. So sites in a protein alignment have some interactions, sometimes distant interactions between amino acids in the chain of residues. So we know this assumption only leads to an approximation, a simplification of the reality, but it works quite well. and it's very useful in order for us to be able to calculate efficiently likelihood values. So when you see sites as independent, when you make this approximation, the total likelihood for a tree based on data that is an alignment of sites is the product of the likelihoods of the different sites, okay? If you see here, the probability of the data is the probability to have the first site times and to have the second site and to have the third site, etc. So it translates into a product of probabilities if you consider the sites as independent from each other. And when you have a product of likelihoods, these likelihoods are the probabilities, okay? And because likelihood values are usually very small, in order to avoid technical issues of numerical accuracy on computers, because computers are not good at dealing with numerical values that are very close to zero and dealing with them with accuracy, computer programs very often use logarithms. So that's why in the results of PhiML, for instance, or AXML, you would very often see results expressed in terms of the log likelihood of a tree and not the likelihood directly. Okay, log likelihood of a tree is the sum of the log likelihoods per site, okay? Because the log of a product is the sum of the logs. So that's why. And don't be afraid, typical log likelihood values, because we said likelihood values are very close to zero, very small, but positive. They are products of probabilities. Log likelihoods are very close, are negative, okay, negative values with a large magnitude, large absolute value. So it's typical to see log likelihood values for reasonably sized maximum likelihood trees of negative 3,000, negative 12,000, negative 100,000, etc. Okay, so when you see this negative sign, it's not. You mustn't be scared that something went wrong in your analysis or in your calculations, or that you're reporting things wrongly. But when you see this negative sign, it means that you're dealing with log likelihoods and not with likelihoods. Okay. Let's have a break here.